So in these set of lectures, we are going to talk about one of the most important topics in traditional AI. Okay? And I'm using my words carefully, because now if you talk to an modern AI researcher, they will not go gaga about logic. 10 years ago, they would have gone gaga about probabilities or probabilistic models, and these days they will go gaga about neural networks. And we will study both of them, right? But logic was considered one of the most fundamental and important topics in AI since the beginning of the field of AI. And we have talked about situations where, our AI founding fathers were trying to prove theorems in logic, trying to solve everything through logic. All of 80s, all of 70s, a lot of 60s and 50s was about logic and different kinds of logic and modeling a problem and logic and showing that in twice settings it gets you what you want to get, etc., etc., etc. Logic was the medium of conversation with an AI system. We are in the world of representation right now. We have been trying to define representations that allow us to explain the problem to the problem solving agent. There is another way we need to represent things, which is knowledge. Knowledge representation is one of the fundamental tenets of AI. Represent knowledge about the world in a manner that it facilitates inferencing. Like I tell you, x is greater than or equal to 5, you sort of know that it can't be 4, it can't be 2, it can't be -3. We don't know what it is. Maybe it is 5, maybe it is 25, maybe it is 2000. But by expressing an assertion about the world, I reduced my space of models that I was considering. I have some variables. Let's say in this case I have a variable x. And let's say I also have a variable y for now. They can take any integer as value. I have many models of the possible worlds. I have many possible worlds, right? And these worlds, each world is called a model for whatever reason. This is just the jargon in logic. So each possible world, like x equal to 7, y equal to -3 is a world. X equal to 25, y equal to -1000 is a world. These are possible worlds of my problem. If I make an assertion like x greater than or equal to 5, I reduce my space of models. Now I know that any model in which x was -3 and y was 25 is no longer valid. Any model where x was -7 is not valid. Any model where x was 4 is not valid. So we have some knowledge about the world. This is how we specify the problem to an AI agent. We tell them some knowledge of the world. Which language do we tell that in? We tell that in typically some language of logic, at least if you are in the 70s and 80s. There are many kinds of common knowledge representation languages. These are called knowledge representation languages. Propositional logic is one. First order logic is another. First order temporal logic is first order logic with an element of time in it. Probabilistic propositional logic, we will study that. Bayesian networks is one example of that. We are saying that we don't know whether it is true or not, but it may be true with probability something. Fuzzy logic, we are saying something else. All of these logics are making different kind of ontological commitments and different kind of epistemological commitments. These are big words. Let's understand them, right? Ontological commitment says, what am I modeling? What are the atomic units? What are the elements of my sentence? The elements of English would be words. What would be equivalent elements of propositional logic? They will be, can you guess? You know propositional logic, Boolean logic. The elements would be propositions. A, B, they are the atomic units. Then you can say A and B, not A or not B or C. But A is a basic proposition, and that is why it's called a proposition logic, fact. So my basic unit is a fact in a propositional logic setting. And what do I know about them? I know that a fact is either true or the fact is false, or suppose I tell you x greater than or equal to 5. What can you say about x equal to 6? It could be true, it could be false, I don't know. And so in our world, I would either know something to be true, or I would know something to be false, or I would not know something to be true or false. Let's say unknown. So if you think about propositional logic, my basic elements through which I make assertions and everything are propositions or facts. That is what I model in my ontological commitment. Propositional logic sits where my ontological commitment is. My ontology only maintains facts. And what do I know about it? That is my epistemological commitment. My epistemological thing means what I know about it. So what do I know about it? I know that it's either true or false, or I don't know. Unknown. Now, let us talk about slightly different logic settings, like first order logic. In first order logic, my element, basic unit by which things get joined is not a fact. How many of you have studied first order logic? How many of you at least know what is first order logic, basics of first order logic? Really? You haven't done any logic course? You haven't done this for every x there exists y such that r x y? You have never studied this? Where have you studied it? Discrete math. So you have studied first order logic. So I define objects, I define relations on the objects, and relations on the objects make facts. Let us think about it again. We have been talking about atomic agent for a very long time. Let's take the example of our class. So earlier we gave the example that if Parth is sitting in chair 25, Vishwajit is sitting in chair 37, Kiran is sitting in chair 49, etc., etc., etc. This whole state I am going to give a number. That is where we started from in the very beginning of the class. And then we said, that's ridiculous. Let us say we make assertions of the we didn't say that, but we can say that we will make facts. Each fact would be true or false. So one fact could be Parth is in chair 25. Another fact would be Parth in this chair 26. Another fact could be Parth in this chair 37. And then specific facts would be true in our state and specific facts would be false in our state. And that would be which logic? Propositional logic. Because each fact is my unit. Now somebody can say this is ridiculous again. Why are you saying Parth is in 25 as one fact and Parth is in 26 as one disconnected fact? It should be connected to the fact that they are both facts about Parth. So let me say Parth is a person and chair is a chair. So one kind of object is the person, another kind of object is the chair. I have 100 students in my class, those become my 100 person objects. I have 150 chairs in my class, those become my 150 chair objects. And then I have a relation sitting in. And this relation takes first argument as a person and second argument as a chair. So this relation is also called predicate, by the way. Predicate, fluent, these are all words of the same feather. Right? So I will say that now this sitting in Parth 25 is my fact. And not sitting in Parth 26. That's also a fact. And when I define my language this way, this is called first order predicate logic. Make sense? So in this world of first order calculus, first order predicate logic, my ontological commitment, what are my ontological elements? objects, relations between the objects, and facts are formed when relations are applied on objects. Right? In the language of AI, atomic agent was a state, propositional definition was state variables, and a specific assignment to all propositional variables gave me a state. So a specific assignment, complete assignment of state variables makes a state. And in first order logic, I have even one level of indirection. I have objects, relations, then I apply relations on objects, and that gives me my state variables, and I enumerate all the state variables, that gives me my state. So notice what I am doing. I am reducing the amount of effort it takes for me to specify a problem by incorporating more and more structure of the real world into my representation. Okay. And what is my epistemological commitment in first order logic? Well, the same. Each fact can either be true or false or unknown. Path is sitting in C25, I know to be true. Path is sitting in C26, I know to be false. Divyanshu sitting in C28, I don't know, because I don't know what Divyanshu looks like. Where is Divyanshu, by the way? He looks like that. So he is not sitting in chair 28. Now I know. So by asking a question and getting the answer, I reduced my model of the world. I asked for some information. I got that information. By using that information, I got rid of all the models where Divyanshu was sitting in seats 28, 29, 30, 35. I know he's sitting in chair 77. And only those models remain. And so on, and so on, and so on. Okay? So, do you now understand the difference between ontological commitment and epistemological commitment? You're learning these terms for the first time. You have some intuition now. Let us look at some other examples. For example, probabilistic logic. You know, when I have probabilities over facts. So, my ontological commitment stays the same. I know in my logic I have facts. We can have the same fact. Divyanshu sitting in seat 26. We can have the same fact. Now, what do I know about it? Let's think about it. Either I know it to be true, I know it to be false, and when I don't know, I might say that I don't know where Divyanshu is sitting, but most likely the person sitting in the chair 26, he is not Divyanshu. Because I have vague memory of what Divyanshu looks like. Now, it is possible that you are Divyanshu. I don't know for sure. But I believe that you are not. So, therefore, I will say Divyanshu sitting in chair 26 is probably 0.1 or something like that. And if I don't know anything what he looks like, I can just say that, you know, the probability that he is sitting in every chair is 1 over 150. I am just being uniformly ignorant. So, the point is, what am I modeling? In logic, I am only modeling true, false and nothing else. I don't know in the middle. But now I am modeling my degree of belief. I know it to be true, I know it to be false, but in the middle, if I don't know it to be true or false, I may have preference of most likely whether it is true or most likely whether it is false. Now, there are other examples. If I say on 23rd May 1975, did it rain in Delhi? A weird question. Now, do you know it? The answer? Somebody knows the answer. Most probably no. What is your name? Kashika says it's May. So it's most probably not. But do you know the answer? You don't know the answer. You're only making an educated guess. You have some belief, degree of belief that, okay, it could have rained. Who knows what happened, what was the weather condition in 1975. They say it has become hotter. Maybe the seasons have shifted, whatever it is. But based on your current knowledge of the world, you believe most likely it did not rain. It is May. It must have been extremely hot. So, but I can ask the similar question that on, 1st December 1975, did it rain in Seattle? And for people who know Seattle will say, I don't know, but most likely yes. Because in Seattle it only rains from August to July. You guys are slow in identifying jokes. You know, once they asked, you know, when does it not rain in Seattle? And the person responded, I don't know, I'm only 4 years old. So, I mean, that's the joke about Seattle. Anyway. So, what is my epistemological commitment? My epistemological commitment is I know to be true, I know to be false, but when I don't know, I still have a degree of belief. And therefore, it is much more expressive than, you know, logic, because logic only says unknown. Then there's something called fuzzy logic. Oh, in the middle you can also do probabilistic first order logic. You have facts, objects, relations, and then probabilities on top of it. And believe it or not, in the late 90s and all of 2000s, this was the rage, or at least one of the most important rages in the field of AI. And one of the leaders of this area in India is our close collaborator, Parag Singla, who is a student of Pedro Domingos, who started this very beautiful famous model called Markov logic networks. And notice the word Markov and logic. It's logic and it's also Markov, which is referring to probability. And there are many other models that came out. Probabilistic relational models came out of Daphne Kohler's group. You know Daphne Kohler? Daphne Kohler was one of the first founders of Coursera. She was at Stanford at the time as a professor. Very, very famous and well-known AI researcher. These are people you should definitely check out. You should know what they stand for. In fact, if you do a course on probabilistic graphical models, a course that sometimes gets offered in our department and in many other IITs and in areas in the world and universities in the world, you will most likely be referring to the book by Daphne Kohler. Okay. So, she and others at the time defined this whole area of statistical relational learning. Again, statistical is a term for probability and relational is a term for first order. Right? Very important stuff at the time. Again, it might come back into prominence, who knows, in the next few years. So, this is about combining probability and logic. But what is this fuzzy logic business? Is it the same or is it different? Now, fuzzy logic says something very interesting. It says that earlier facts could only be true, false or unknown, but now the truth itself is fuzzy. Like I ask you the question, what's your name? Harkirat. Is Harkirat tall? Now this notion of height and tall specifically, can you specifically say that this is true or false? Well, if he goes to China, he might be tall. And if he goes to the US or Australia, he might not be considered tall. But notice that the concept itself is a fuzzy concept. You know, here's another beautiful example. You know, you take two puppies. One of them who is red and another who is brown. And you close your eyes, you put them in a box, you close your eyes, you take out a puppy and you don't know whether this puppy is red or brown. Is this fuzzy logic or probabilistic logic? Probabilistic logic. Right? I don't know whether it is true or false, I don't know whether it is brown or red, but it's either brown or red. Now we allow them to mate. Let's say they are of opposite genders. And lots of puppies come out. Then I take this puppy out and look at the puppy and ask the question, is this puppy red or brown? Now, is this propositional logic, fuzzy logic or probabilistic logic? This is fuzzy logic. This is not neither red nor brown, it's somewhere in the middle, it's probably 0.7 red and 0.3 brown. When your truth becomes non-binary and a number, then you get into fuzzy logic. But you can still not know it. You can still close your eyes and take a puppy out and ask the question, is this puppy red or brown? And in this case, it will be probabilistic fuzzy logic. So now you are able to see the difference in your commitments. Now I shall point out that fuzzy logic has gone sort of out of circulation. It was the big deal in the 80s. You must have, or at least your parents have heard about washing machines which have fuzzy logic in them. You may not hear this term anymore because those things are passé, but when I was a kid, it was a big thing. Washing machines has fuzzy logic in it, Japanese, right? Fuzzy logic was considered one of the ways in which the problems of logic can be solved, and we will talk about the problems of logic when we come to probabilistic models. But over time, this has gone out of circulation because people found some technical inconsistencies in fuzzy logic and other kinds of things came up which became important. I would point out that while when I was growing up as an AI researcher, as a student and so on, nobody used to talk about fuzzy logic where I was. Some of the ideas of fuzzy logic are starting to become useful in neural networks. So, you know, the world comes full circle. When I was a student, nobody used to talk about neural networks. Now everything is neural networks. Nobody used to talk about fuzzy logic. They still don't, but some ideas have been taken. For example, if I have a variable with truth 0.7 and another variable with truth 0.5, what is the truth of the conjunction of these two variables, A and B? This is a question that fuzzy logic has to deal with because my truth is always fuzzy there. And so now I have to talk about output of A and B, A or B, not A, and so on and so forth, and you have to have a real valued answer for everything. And all of those ideas have become extremely important in neural networks. Anyway, we won't go there. I shall also point out there is one other thing which you will not study, which became a big thing but is no longer that big a thing, called non-monotonic logic. So up until now I have been telling you, you give me a new fact and I reduce my space of models. But can it ever happen that you give me a new fact and I increase my space of models? If that happens, it's called non-monotonic logic. For example, I tell you that I have a bird or an animal. Let's say I tell you I have a living being. Say it could be the people tree, it could be a human, it could be an eagle, whatever, right? I have lots of models. Then I tell you this living thing is a bird. So now suddenly you have reduced your space of models and you say, okay, I know if it's a bird then it flies. So therefore I have reduced my space, gotten rid of the people tree and a human, and I have reduced a space of models and I can sort of say that it flies. Because I know that if it's a bird, it flies. But then I tell you it's a penguin. And as soon as I tell you it's a penguin, you say, oh, it no longer flies. What did I do? Basically, I told you something that if it's a bird, it flies, but then I gave you an exception. This happens mostly except when it's a penguin or an ostrich or something. So when you do this logical reasoning, then every time you get a new fact, you start making assertions, but then as soon as you get a new fact, which is an exception fact, then you go back on your assertion. If you have this kind of a phenomenon, then this is called non-monotonic logic. Now in your brain you must be thinking that there may be other ways of dealing with it, and we are not getting into the details. I am just giving you the term non-monotonic logic just for your high level understanding. And there are many different kinds of knowledge representation languages: propositional logic, predicate calculus, frame systems, certainty factors, Bayesian networks, influence diagrams, ontologies, semantic networks, concept description languages, non-monotonic logic, fuzzy logic, description logic. There are just too many of them. Okay? And of course, in our class, we will only be studying propositional logic, and then probabilistic propositional logic will be Bayesian networks. So this whole, most traditional AI courses will go at depth about first order logic, but I am taking this executive decision that we don't have to cover it, because in the modern world those ideas are not the most important ideas that we need to worry about, but still you have to have some high level understanding. Okay? And what are you going to study? Well, basically what you are going to study is, I will give you some true assumptions and then you have to deduce true conclusions, and that's the basic idea of logic. And what is true This is a philosophical question and we will never talk about it. True means 1 and false means 0, and that is sort of what we are going to talk about, right? We are computer scientists. At one step up you can become a philosopher, and then you can say that, you know, truth is, we know truth only by reason, sometimes we know truth by heart, nothing more powerful than the truth, and you can start debating about what is truth and what is not. For us, it's just value 1 is truth, okay? I think this is a good point to stop. In the next class, we will start talking about different components of a knowledge representation system as they are studied in the logical framework.